Hi everyone, I'm Nicolo. I'm a software engineer at DataStax. I'm very happy to be here today, and I'm going to talk about scaling unstructured data indexing with Apache Pulsar. A little bit about me. I'm involved in the Pulsar project, whereas I'm a PMC member. I'm also involved in Bookkeeper, which is the data storage project for Pulsar. I'm also an Apache Software Foundation member. And my background is basically around streaming, databases, cloud native applications, and generative AI. And today I'm going to try to mix streaming and generative AI and see how streaming can help generative AI workloads. So let's get started. So if you think about generative AI, I think anyone is comfortable today to talk about ChatGPT. So you have a chat, you can ask questions and you get a response that appears intelligent. It seems like you are talking with a human. But how it works under the hood? So there is a LLM, a large language model, which is basically able to, given a request, to produce and generate a response. And normally you call the request prompt, and prompt are normally compounded by two parts. The first one is the instruction. So you tell the LLM what you want to achieve, what they have to do, and then you add a question. So normally you might want to set up a chatbot for your product. Let's say your product is has a documentation page, and you want to help people starting to understand better your product. So you add a chatbot in the web page, and in order to set up that kind of chatbot, you need to instruct the chatbot on what they have to do. So you might say you are an helpful assistant expert on this product, and you might, add more instruction, more details, and then you append the question. So whenever the user asks a question, you generate a new prompt with the user question plus the instructions, and that works. But it's very likely that your product is not part of the trained data that has been used for training the LLM, because the LLM has been trained on some data, some static data that have not changed since their inception. So when a new LLM model comes out, it's already out of date because it doesn't have access to internet or to any other knowledge. So what you normally do if you want to instruct the model to know about your product or whatever you want to let him have access to, there are two standards that are coming out today. The first one is fine-tuning. So normally fine-tuning is a good option if your data is still static. So for example, fine-tuning works like I get the model, I choose one model that I like or is particularly performant on some kind of operations, and I instruct him with a dataset, and the dataset, I need to generate the dataset based on the product documentation or the product characteristics. Once I generate the dataset, I train that again, and I get a new model basically. And if I ask the same question to the new model, it's going to know more about the product and the dataset that I sent to him. But this presents a couple of challenges. The first one is that every time the product changes, let's say you release a new feature, you need to train the model again, and you need to fine-tune again. And that means create a new dataset and start over all the process. And another problem is that if you have another product, you need another dataset. And so it's like very specific for one single task, but once you want to reuse that model, it's not gonna be like the best solution. And the alternative is called RAG, Retrieval Augmented Generation. And so the idea behind RAG is that instead of you training a model, you use a model which is very generic. It knows a little bit of everything, but is not really into the details of your product for sure. Maybe your product is not even public, so it doesn't have any clue about your product. So what you do with RAG is the essential point is that when you generate the prompt, you add another step, which is called context. And basically with the context, you insert domain specific data. So you set the instruction, you set the question, but also you instruct the LLM to say, okay, but this is some properties about the product that are related to the question of the user and the product. So the LLM and the model remains static, so you don't train the model. So if another user comes, you need again to insert the domain specific data. And the important thing is that you cannot put here all the documentation of your product, and that's normally because models have a context length which is very limited, and even new models like Gemini Pro, they have a larger context length, but the problem is that it increases costs and latency, and so it's a hard limit. And so with RAG, you send the contextually specific data when you generate the prompt for a single question. And RAG in general is an architecture, is a specification, I would say that. And so if we think about our chatbot and if we want to build it, we have the prompt question, we want to build the prompt, we want to query the LLM, and we need to insert the domain specific data. And those are all the objects that we need, but how do we connect the dots? So RAG tries to let you generate an application and workloads that can be sufficient to create this kind of applications. So how do we connect the dots? So the first thing we need is to perform similarity search. Why similarity search? Well, because given a user question, we want to get relevant data about our product. And normally what you have is that you have a lot of, let's say, web pages or PDFs, some static content that are unstructured. So what you want to do is you want to chunk and split all the text into smaller parts, and based on the user question gets the more relevant documents. And similarity search is not new, is a technique that has many years, but it's very helpful in this case. And so in order to perform similarity search, you need a vector store or vector database. And vector databases works with embeddings. And basically embeddings are the way that the vector database uses to compare two texts. So when you convert text into a vector using into an embeddings using into a vector using an embeddings model, what you really do is you get a string, you get a text, and you generate a list of float, okay? And the float represents that text in thousands of dimensions, and the number of dimensions depend on the embeddings, but that is not important. That is just a detail. The important thing is that you can index all the text, the small chunks, into your vector database, and given a user question, you can retrieve the most relevant documents, and you can pick 5, 10, 50, depending on the use case. So the next piece that we need is how do we generate those embeddings, and we need an embeddings model. And normally you can generate embeddings in two ways. One is hosting a model locally in your machine, and normally you need a GPU optimized machine because they use a lot of GPU resources, or you can use API inference endpoint. So someone else is offering you as a service, you just call an API via HTTP or gRPC, whatever, passing a text, and you get the list of the floats. So this process is called the compute embeddings, and this is the whole picture. But if we look into that, we see that there are two different processes. The first one on the left is indexing. So you get all the domain-specific data about your product, and you compute the embeddings about the single chunks, and you want to store the embeddings, and you do that in a vector database. Within the same vector database, and given the same embeddings model, when the user asks a question, you are able to compute the embedding of that question using the same embeddings model. You are able to perform a similarity search using that vector, and you are able to then to construct the prompt with the top 10, top K most similar documents for the user question. And then is how you implement RAG. So in this talk, I want to focus more on the left of this chart on the indexing part, because it's the way is the point where streaming and Apache Pulsar can really help. So if we focus on the indexing, we can split the whole process in 4 steps. The first is load. So we load data from some sources. For example, a PDF, some static content. We scrape a website. Let's say we have the product documentation website, or we can have a database, NoSQL or SQL database, doesn't matter, or an object storage. We could have a log storage. And the important thing is that we get data, and we can have actually 2 kinds of data. One is unstructured, like a PDF, a lot of texts that we need to split and chunk in chunks. Or we could have a schema, structured text data, when we have a schema and we know all the fields, what they represent. Okay, but anyway, we need to parse this data, we need to extract the text, we need to normalize it, and we need to apply filters. Maybe we want to filter out some languages because they are not relevant for the user. And then the last step is we want to split into a lot of chunks. Given in big document, we generate different chunks, several chunks, depending on the chunk size. Once we have that, we have those chunks, we need to generate embeddings for each of those. And I talked about text, but it could be also for images or media types. There are more advanced techniques like contextual interaction that is implemented in Colbert, but the result is the same. We just want to generate embeddings, store them in the vector database, so we can retrieve them based on the user question or the requests. And the last part is indexing. So we actually write to a database. Another important thing is that along all the process, given the initial chunk, we may want to store also metadata. And that is a very important feature to get it practical. So if you think about a web page, we read all the text from that web page. Maybe we generate 10 chunks. For each chunk, we want to save the URL of that web page. Why? Because maybe when we retrieve, then we can say like, if you want to find out more, let's visit this page. And we have the URL. This is a very practical example, but there are tons of use cases for metadata. And today, what I see in the market is everyone is trying to building this kind of applications, but since this comes from a data scientist world and is being converted to our engineering world, what is happening is that everyone's building that as a monolith application. Mostly in Python, but doesn't matter the language. The fact is that it's monolith. And that means, like every other monolith application, is that you face some challenges when you go in production with real data, with higher volume of data and more things to index. And so the challenges are always the same. You need to scale more, you need to reduce costs, you need to have higher performances, SLA, and everything. And one important thing is that in this case, since this is a early stage of this technology and world, most people and most users are trying to find the best setting for their RAG applications. And that means you want to try the same from the same data set. You want to try different parameters during the process. Maybe you want to change the embeddings model. Maybe you want to evaluate the chunk size or the way you extract the text from a PDF. Or maybe you want to try different vector store and the similarity search algorithms. And that means maybe you want to index data, the same data over and over and evaluate the results and the relevancy. But you need a short feedback loop time. Otherwise, it's very hard to find a better solution, and you end up going with the first or the second solution that you try, and might be converted, and might be that you need to pay more, or you need to you have low throughput, and you might have higher latency. Like, you can pay more, you will end up paying more and having worse performances in general. So how Pulsar can help, and streaming in general, but Pulsar has one thing that other streaming processing libraries and platforms don't have, and it's Pulsar functions. So I reimagine the whole process using Pulsar functions and using Pulsar in general. So if you're not familiar with Pulsar function, it's a serverless framework for building applications, and you have three kind of function. The first is the source, when you read data from some remote source, and you push that into Pulsar in a Pulsar topic. The function reads from a Pulsar topic, do some lightweight processing, and push to another topic. And the sync reads from a topic and push to an external system. Okay, so if we take the first step that we were seeing before, we can create a Pulsar source using that both manages the load and then parse steps. And so normally, I was saying that most of those applications are monoliths and are written in Python. And why they're written in Python? Because of the ecosystem. Ecosystem is really most of the applications and most of the libraries and frameworks are in Python as of today. It might change in the future, but as of today, if you build something and you start with LangChain, Llama Index, or any other framework, it's likely that you need to write it in Python. There are alternatives for sure, but if I had to do it today, I would choose Python for the source part. And that's because also you load the data, but the most difficult part is parsing the data in a reliable way. And again, there are a lot of frameworks to do that, and libraries that are optimized for this kind of operations. So let's say you start with Python. So since Pulsar functions support both Java and Python, you can pick whatever you prefer, but you can do it in Python. So you load data from a remote source, and you parse it, and you create chunks. And you can attach metadata to chunks as well. And you push each chunk as a Pulsar message in a Pulsar topic. And then you create a Pulsar function that reads from that topic, and you try to embed the text into a vector. And normally, the embeddings, as I was saying before, could be local, so you run a model locally, or you call an API. And normally, the API is just HTTP traffic, and so it's a lightweight operation in that case. And here, what really could help is using batching because most of the providers support batch of embeddings. So you can save cost and reduce latency, of course, and reduce the network calls and all the ops that this involves. Once you get the embeddings, you write to another topic, and from that topic, you read, and again, in batch, you can write to the vector store. Basically, you can imagine a write to vector source like an upsert, and using upsert means that you can also delete stale data. Let's say you update a web page, you can delete all the chunks of all the stale data that are not there anymore. And this is very handful if you write a Pulsar sync, because most of the application is already handled by the Pulsar function framework. So I know it could sound costly, but if you think about the experimentation phase, if you want to restart and you want to replay data from the source, you don't need to reparse everything. Or if you want to use the same embedding model, try different vector store, try different setting in the vector store upsert operation, you just need to restart the sync. This is a microservice architecture, and there are many benefits in that, like reducing costs and latency. Another approach that you could take here, if you don't really, if you think that is overkilling, you could package together the function in the sink into a single sink, whereas you get the chunk as a text and plus metadata, and you compute the embeddings and write directly to the vector store. This could be another approach that has different trade-offs, but yes, so Pulsar function allows you to do both, and in a very easy way, actually. And so how we solve those challenges that we were seeing before. So first of all, we have already a Pulsar function, a serverless framework out of the box using Pulsar. Scalability, this is a very important point. If you think about these steps, they are very different workloads. Like the load and parse operation, mostly the parse operation is a CPU intensive operation. So you need to parse a lot of text, and you need some kind of machine, CPU optimized machines, differently from the embeddings and the vector, the indexing part, whereas you might need just a normal machine because you're just doing network calls basically. So if you want to scale only one part and you need more resources only on the CPU, about the loading and the parsing step, you just spins up and change the parallelism option in the Pulsar source, you are done. You don't have to worry about, okay, this means I need more powerful machines for the sink or more machines for the sink and the function too. And another use case is if I'm building the embedding, computing the embeddings locally, I really need a GPU power, like a GPU optimized machine. And so if you think it as a monolith, you end up with a very powerful machine that doesn't scale out basically, because it adds a lot of costs, because you need GPU for the embeddings computing, and you need probably CPU, but yeah, already the GPU part is already a win if you use Pulsar and Pulsar function. And another point is for sure cloud native. So you are ready to go in production in a Kubernetes environment or any other cloud provider, and you don't have to worry about the deployment part because it's already handled by Pulsar functions. And again, if you save costs in the sense that if you want to replay data, and if you want to, again, the scalability and the costs are very tied together, because if you can scale better, it will save costs. And if you want to replay some kind of data and not the whole pipeline, it's a win-win, because you replay only the data that you need, and you can replay them in parallel. You can use your fantasy to generate workloads from the same data source, which is the Pulsar topic. That is the output of our Pulsar source. And performances as well comes with costs and scalability and evaluation feedback loop time. As I was saying before, there is still an experimentation phase for generative AI workloads and RAG in general, when you want to try different settings to get the best accuracy and relevance that you can. And having shorter feedback loop time means that you can try multiple things and different things, even with the real production data that you might not want to embed multiple times because of the cost, because of the time. And this is not is a solved challenge if you're using this kind of architecture. Now, all this architecture is not only a part of my imagination. So it's something that you can build today, and something that I believe people are not yet ready, and they are not seeing this kind of architecture as the V2 of generative AI applications yet. But I'm sure that this year or the next year, this will come as a use case for Pulsar and messaging in general. So in order to prove this kind of assumption that I made here, a couple of colleagues and I, we built a framework, an open source framework based on streaming and Pulsar as well, and Kubernetes for building generative AI application for running them in production and address all the challenges that we are seeing today. And the name of the framework is Langstream, and it's not just Kubernetes and streaming, but it provides a lot of built-in things like declarative generative AI pipelines, and not only the indexing part, but a complete RAG application. Is Apache 2 licensed, and there is an open community with discussion and roadmap, like is the real open source project. And that was it. I hope you find the content interesting, and thank you.